Hello guys, this is Code and Code and this is a video lecture for Tarjan's algorithm for strongly connected component. We have already seen Kosaraju's algorithm for strongly connected component, and in this lecture, in the recent 2 or 3 lectures, we will be studying Tarjan's algorithm, its implementation, and how this is different from Kosaraju's algorithm. So let's get started. So what is strongly connected component? You might already know, but for those guys who do not know, a strongly connected component is basically a subset C of vertex set. When you have graph, you have a vertex set and an edge set, right? So strongly connected component is a subset C of vertices such that for every 2 vertices in subset C there exists a path in the given graph. So if you choose 2 nodes from subset C like V and U, then there must exist a path from U to V as well as V to U, because we are here talking about directed graph. In undirected graph, a path from U to V confirms that there is also a path from V to U, because the path is actually undirected, the edges are undirected. But in directed graph there must be a path from U to V as well as V to U. So this is the definition of strongly connected component which we are studying how to find. So for this given graph 1 2 3 4 5 6 7 8, there are 8 vertices, and we can see there are 3 strongly connected component. This 1 2 3 node forms a single strongly connected component, 4 forms a single SCC. Similarly 5 6 7 8 form a single SCC, because if you choose any 2 node out of these 4 nodes like 5 and 8, there exists a path from 5 to 8 as well as 8 to 5. For example, from 5 to 8 there is this path, from 8 to 5 there is this path. So if you choose any 2 node in a single strongly connected component, that there exists a path from A to B as well as B to A. So there are 3 strongly connected components. The problem we have is to find the number of strongly connected components. Sometimes you may also be asked to actually print each SCC in a new line. So you will be printing 1 2 3 in a separate line, 4 in a separate line, 5 6 7 8 in a separate line, indicating since there are 3 lines, that means there are 3 strongly connected components, and each node in a single line, all of the nodes belong to a same SCC. Now, Tarjan's algorithm and low link value. We have already studied about low link value, where we were studying bridges and articulation point. In graph theory part 1 course, I have bridges and articulation point, how we can find that, and there we have talked about low link value. Tarjan's algorithm heavily depends upon low link value. So let's study again what is low link value. If you already know, you can simply continue. So for each node U, low link value is defined as the ID of the lowest ID of the node reachable from node U. You have node U. From node U you can reach to multiple nodes. Multiple nodes are reachable from node U through DFS, and low link value of node U will be the ID of the lowest node you can reach. And ID doesn't mean the if there are 4 nodes 1 2 3 4, so node 1 has ID 1. No, it is not ID. If you are coming from those lecture where we have studied articulation point, or we have studied arrival and departure time, right, in out time of graph or a tree, so in time is defined as the ID. If you haven't studied those lecture where we have studied in out time and the articulation point and bridges, then you might not know what is in and out time. So I would highly advise you to go through those lecture which are there in graph theory part 1 series, and study what is in out time, because in time or arrival time is actually the ID of each node. Now if I explain you by an example what is how you will calculate low link value, though it is exactly the same that we have studied in articulation and articulation point and bridges lecture. So suppose these are 4 nodes and this is your graph. A B C D are the 4 nodes of the graph. I started DFS from node 1. Now if you node A, sorry, so since you arrive node A at time 1, so it's here you see numerator and denominator. If I explain this as a fraction, numerator represents the arrival time and denominator represents your low link value. When you reach certain node, its low link value is initialized with its arrival time. So arrival time or in time is 1, so it's a low link value. Now from this node you can minimize its low link value using the out edges. So Here you see from node A there is one out edge to B, so you would make DFS, since B is not already visited, so first you would make DFS call to it so that it can calculate its low link value. Then using its low link value you can reduce or minimize your low link value. So there is an edge from A to B, but B is not visited, so you would make a DFS call to B. Since you reach node B at time 2, that is why its low link value is initialized with 2, and so is its arrival time. From B there are two out edges to D or C. Suppose both of them are unvisited. Suppose from B we made a DFS call to node C, so in time and arrival time are initialized with 3 and 3. Similarly from C there are two edges to A or to D, so suppose we went to D, arrival time and low link value have been initialized by 4, 4. Now since from node D you cannot go anywhere, so this is its final low link value. From here you would return, so from here you return to node C, right? Now since node D have been you have completed the DFS call of node D, now you can use node D to minimize your low link value. So since there was an edge and node D was not visited, so you made a DFS call. When you will make a DFS call, after that you would minimize your low link value with its low link value. So 3 low link value of C is minimum of low link value of C, comma low link value of D. Low link value of D is 4, it is 3, so of course nothing would happen. It would still be having this low link value as 3. Remember, when you are on certain current node and there is an out edge, there are two possibilities. First, the out edge is going to a node which is not visited, and second, out edge is going to certain node which is visited. So if it is going to a node which is unvisited, what you would do, you would first make a DFS call, and after you return from that DFS call, you would minimize your low link value with that node's low link value. But when there is an edge from you to certain node which is already visited, see here, for node C, A is already visited. If you look at this edge, right, and this is visited, so what will happen? Now you are not allowed to minimize your low link value with its low link value, but with its ID or arrival time or in time. So you would minimize the low link value of C with ID or in time of node A. So minimum of 3 or 1 is 1, so low link value would update to 1. Now you have traversed this edge as well as this edge, nothing to traverse here, so you would go back, right? Now you are at node B. Now see, it has completed its DFS call from here. From B you made a DFS call to C, right? Because C was not visited, so you made a DFS call to C, and now that call has completed its execution, and now you can minimize your low link value with its low link value, right? Because for node B, C was not visited, so you made a DFS call, and after DFS call what you would do, you would minimize your low link value with its low link value, right? Because it was not visited, so low link value of B would be updated to 1. Now this edge have been completed its work. Basically you have completed the task of this edge. Now there is one more out edge for B, which is this. Now this is already visited, so what you would do, you would minimize your low link value with its ID or in time. In time is 4, so minimum of 1, 4 is 1, of course, so nothing would happen here. So both of the out edges have completed their work. Now from B you would simply return. From B you would return to A. Now since B has completed its execution, so A would try to minimize its low link value with the low link value of B, which would not change anything into A because its low link value is already 1 and its low link value is again 1, so nothing would happen. Finally it will return to main function, from where we have made a DFS call to node A. So here you see 1, 1, 1 and 4 are the low link values. Now looking at this graph, the whole graph has completed and all of the nodes have completed calculated their low link value. Now ask these questions. First, how many strongly connected components do you see in the graph, and how many different low link values you see? You see there are two SECs. First, this forms a different SEC, and these three nodes form different SEC. So in total there are two SECs, and how many different low link values you see? You see there are two different low link values, 1 and 4. So if there is any connection between low link value, the count of the low link value, and the number of strongly connected component, Well, there may be, we do not know. Second question, is there any relation between the nodes in the same SEC and their low link value? For example, A, B and C all lie in the same SEC, and what is their low link value? 1, 1 and 1. Again, we see certain connection between low link value and SEC, right? So it is possible that yes, all the nodes in the same strongly connected component have same low link value. If that is true, all you have to do is run DFS to calculate low link value of each node, and then keep track of how many different or how many unique low link values exist there. If there are X number of low link values, then there are X number of strongly connected component. If this is true, that each node in the same SEC have same low link value. If this fact is true, then you can do that. But the question is this is true? Let's see a counter example. So the problem with low link value is this. See, the low link value heavily depends upon the order of DFS. In this graph, what we did from main function, we did a single DFS call to node A only, and that was able to traverse the whole graph. Sometimes what you have to do multiple DFS call from the main function for whole graph to get visited, right? So suppose if instead of making a DFS call to node A, we made DFS call initially to node D, what would happen? Oh, it's in time and low link value would initialize with 1, right? And after that, there's no way you can visit other nodes, so you would return to main function. Only D have visited till now. The rest node are not visited yet. So in second time, what you did, you made a DFS call to node A this time. If you made a DFS call to node A, all of these 3 nodes A, B and C will get visited. Now see here, all of the 4 nodes are having same low link value. Remember the first question. And now you see there are clearly multiple, there are actually, to be precise, there are 2 strongly connected components, but still there is only a single low link value. Again, 2 nodes which are not in the same SEC are having same low link value. Like take any node from this SEC and this, right? Like C and D, they do not belong to the same strongly connected component, but still their low link value is same. This is the problem with low link value, and that is where Tarjan's algorithm kicks in. It defines a criteria when you are going to update your low link value with other nodes. It keeps track of certain node, valid node you can say, from which you can update your low link value. Suppose you are going to update your low link value using low link value of D. There is a list of nodes from which you can do that. So you wanted to update from D, so you would see whether in that valid list D exists or not. If D doesn't exist in that valid list, then you won't be updating your low link value. So now Tarjan's algorithm imposes a restriction upon from which nodes you can update your low link value. And how we do that, we'll be studying that in the next lecture. So this was all for this lecture. I hope you have understood the concept of low link value and how this can be helpful as well as messy at the same time, and how in the next lecture we'll be seeing how Tarjan's algorithm actually helps us to define a criteria based on which you will be able to get this. All the nodes which are having the same SEC, all the nodes which belong to the same SEC will have the same low link value after we apply the restriction suggested by Tarjan. Also, if there are X number of different low link values, then there will be X number of strongly connected components. Again, this will be true after we apply the restriction suggested by Tarjan. So that we'll be studying in the next lecture. Thank you guys for watching, and till the next video drops, keep coding. Thank you.